right. And we're teaching mathematics in this department. So first, mathematics, I want to say that the ultimate goals of mathematics instruction are the student to understand the material and apply the skills and record the concepts in the future. And there is no benefit for the student if they just memorize the formulas and the procedures and to prepare tests for tomorrow. And so because of that, we would like to introduce some fun and hopefully the student could consider mathematics are fun and think them brainstorms and focus on the concepts. So our goal is trying to make a student like mathematics and develop some kind of skills and to handle apply mathematics in their life. For example, sometimes I give a game in the student. I say, let's play a game. I can tell your age using your shoe size. Then I'm going to give them a procedure saying, start with your shoe size. If you have half size, round it up. And after that, multiply your shoe size by 5, then add 50. And after that, multiply that number by 20 and add 1025. And then subtract the year you were born and add 1 if you already have your birthday. Then the final digit, the first digits are your shoe size and the last digits are your age. When students play this game, they will do all those calculations and get the answer. Their eyes will become bigger and say, how did you get it? So we'll ask them, here is the reason. You set X and Y, and so go through all the mathematics calculation. And then they realize this is not just a game, it's a mathematical deduced that what is their shoe size or what is their age. The next thing is we help students to do visualization. For example, I ask a student, a cube is painted from all sides. It is then cut into 27 equal small tubes. How many cubes has one side painted? How many have 3 sides painted? And then they will learn to visualize. And if they visualize, they can see that only the center of each face has one side painted, and the small tubes in the corner have 3 sides painted, so they can obtain the answer. And then sometimes I ask the student to learn how to see the patterns. For example, ask them how much energy will the newest solar panel gives. And then they will see the different panels have different cells, and also the number of the voltage there. And the question is, what is the voltage for the last one? And so students need to look at the figures and identify what are the patterns. And you notice the cells is the columns identify the first 2 digits, and the total cells identify the last digits. And so the student use this can learn the patterns. And then I show the student how to think out of the box. For example, ask them, what is the next number in this sequence? And students think and think, they do not know the answer. But ask the student to read the elements out loud, 1, 1, 2, 1, so on, so on. Students understand the sequence actually is how you read the numbers. The red number is 3, 1, 2, 2, and the 1, 1. That's how they get the patterns. Finally, ask a student to critical think. And for example, the woman says, I have 3 daughters. Their age are whole numbers. And the product of the age is 36. And it's not useful to tell you the sum of their ages. And my oldest daughter likes dogs. what are the ages of the children? First, the student think, is this a real math problems? But then you ask them to read exactly each sentence. It says, the numbers are whole number and the product are 36. So you factor 36 on the first row, and there are so many combinations. And then add up those three factors, and it's not useful to tell you the sum of their ages. Not useful means they have to be repeating. The sum is 13. So it is either 166 or 299. And then they say, it's my oldest daughter like dogs. So that means there is an oldest one. So the answer has to be age 229. So with this, you can help students develop their critical thinking skills. So after students learn to answer those fun mathematics questions, they began to ask themselves, how could they miss something so easy? Most tricky questions are designed to tease their mind, promote their logical reasoning and analytical thinking skills. And next, my colleague, Dr. Presho, will present his part.
All right, excellent. So yeah, we have like a dual presentation today. So I'll jump right in where Dr. Wang left off. So the motivation for the type of project that I'm introducing here, rather briefly, would be this notion of calculating integrals by hand or by using computers, in a nutshell. So for instance, in this case, sometimes this process is rather daunting, kind of a pain, for lack of a better word. And it's just an alternative for students to see how the usage of computations, computers, can help aid in their computations. So as an example, I was probably a little too heavy on the math computations here, but even before I start this, let me say the main idea, what I wanted to show is that doing a problem like this by hand is like kind of in depth. It's like a high level calculus 2 problem. But nonetheless, this would be an example where we talk about the arc length of a curve, which has some real world usage as well. And in this case, we would plug it in to a tried and true formula, which amounts to a definite integral of calculus 2 quality. And this integral actually is a little bit, I don't know, more in depth, a little harder than some integrals they may see before. So we would have to do a clever, essentially U substitution in order to compute this. Then from that U substitution, we would finagle the values a fair amount, and we would want to rewrite everything that was previously X based in terms of U quantities. But then once we've written the actual argument integrand in terms of U, we then also have to rewrite the limits in terms of U as well. But I want to emphasize the larger scope is, wow, it's kind of a multifaceted integral to do by hand, rather lengthy. But at this stage, once we have the integral, where we translated everything in terms of U from the original X, now we have to do yet another Calc 2 base trick here, which is called I think partial fraction decomposition. And then we can finally, after kind of some painstaking detail, come up with a system that we can now solve, integrate exactly. And in this case, this is the reason I chose this type of example. Even the quote unquote exact solution is kind of gross. And that's one reason I like this problem. In the real world, in principle, even though this value is exact, it has irrational numbers all over the place. So we would have to plug it into a calculator or a computer anyway to spit out the decimal form. So for all those reasons, that's why this is a really good motivational tool to say, hey, we're going to need to use a computer anyway. Even from all of that daunting handwork, we're going to have to plug it into a calculator or a computer to find the answer, to find the number anyway. So this becomes a motivational tool for the use of numerical integration techniques, one of which being Simpson's rule. And ultimately, I wanted to show two slides here. and then we'll kind of ease out, see if there's any questions, but at this stage, Simpson's rule basically just allows us to compute an integral to arbitrary level of precision by using precisely that original integrand. So there's no inherent substitution, there's no inherent partial fractions, it's very like cut and dry. And ultimately, what I've done here is just taken a screenshot of the Python code. I have them write their own code, but we're talking about 20-ish lines of code, which for all practical purposes is faster than doing the integral by hand. And in addition, now you can do Simpson's rule calculations for a large range of integrals. So this little code, which again, in terms of time spent, is analogous to the time spent on the hand computation, but it's much more robust. Yeah, and then what we have them do is tabulate, out some tables you would see in many kind of mathematical type papers, even though this would be a new idea. But in essence, what we end up showing them and them showing themselves, I guess, is that for a very moderate Simpson's level approximation level, we end up with a solution which matches. Here I chose 9 digits, but we could do arbitrarily more. But in this case, it's like using this code, hitting enter from all the magic you've created will immediately give you your solution to an arbitrary level of precision. Yeah. And in this case, again, just some student outcomes. This is the part I don't want to dwell on too much. But really what it does, right, it allows students to review calculus first and foremost. That's completely essential for undergrad math students. But then it allows them to take the next step. And in my experience, computational mathematics does bridge more on graduate level mathematics. So this becomes like a bridge from undergraduate to graduate mathematics in some ways. Perfect. And here I just wanted to show a few figures. Students really seem to like this type of project. So for instance, in spring 2023, which is the first semester I introduced this, we're talking about 4 out of 5 student responses, meaning they agree that this type of project is suitable for what they're trying to do. And then I taught it 2 years later, and in essence, the students did still like it very much, seemingly. And in fact, it would be an increase in terms of that average value from one semester to the next. So that's where, yeah, I think my time is up. We'll end. And thank you. If there are any questions, we'd be happy to address them.